Hello and welcome to the Daily Space for Friday, July 6th, 2018. As often occurs, I am your host, Dr. Pamela Gay, and I am here to put science in your brain. I'm going to do a quick roundup of some of today's science highlights from astronomy and space science, and then I will be here to answer your questions. Following this show, I will be handing the channel over to Dr. Matt Richardson and Big J. Dr. Matt is working on teaching Astro 101 to Big J and invites you to join in as one of our computer scientists learns astronomy. So, in today's first news story, I have a tale of planetary nebula. These particular kinds of objects are formed by stars like our sun in their final days. The stars eventually hit a point that we call asymptotic giant branch red stars. And in this phase, they have bloated out and only loosely hold on to the outer atmosphere of the star. As this phase ends, the star is no longer able to keep doing nuclear fusion in its core, and when this happens, the core collapses down to a white dwarf, a stellar remnant about the size of Earth's moon with a mass not too different from our sun, and the outermost layers of the star drift away to create amazing nebula like those that are pictured here. These three particular planetary nebula were observed with the Hubble Space Telescope's WIFPIC-2 camera. This was the first high-resolution, fully functional camera that was put on Hubble, and all of its data is now available through the Hubble Archive. This means that researchers, such as those that worked on this project, where this research was done by D. Baria and S. Kimswenga, who are from Chile and Austria, respectively. These researchers were able to go through the Hubble Archive and pull out already existing data and utilize it for a new analysis that may never have been imagined by the original observers when they asked for the telescope time. This kind of research is why it's so important to make data freely accessible after the original researchers have had a chance to do their research. In this case, what they were doing was working to model how exactly do you create structures like this. One of the reasons that the Hubble Space Telescope was launched and created was to study planetary nebula. Prior to Hubble's launch, all we knew was there were these weirdly shaped, kind of fuzzy, blobby objects in the sky that were distinct from supernova remnants, and we didn't understand very much about exactly what they were or why they were structured the way they're structured. With amazing images like these that were achieved by the Hubble Space Telescope, we were able to map out the fine details in these systems and realize that, well, in this case, the red is the nitrogen in the images. The helium, which is the hottest gas, is shown here in blue, and that dominant green color comes from oxygen 3. This is oxygen that has had 3 of its electrons removed. Now, these particular objects are also interacting with the gas and dust that surrounds the place where the star initially died. And located deep in the core of all 3 of these systems is a point of light that is that point where the white dwarf star exists. What they were doing with this particular model was, with this particular research, was building models that would allow them to look at these systems and determine their distance by figuring out what physical sizes are required for each of the different shock levels. These are multi-shelled systems where you can see that the helium forms one particular shock level. The Oxygen 3 is another shock level. The red nitrogen is yet a third. So with these three different temperature regions, with these three different sets of physical parameters that are required to create the color and density of the gas that we see, they were able to model what physical sizes are needed, what ages of the systems are needed to create what we see. By figuring out how big the objects must be physically and comparing that with how big they appear to be on the sky, scientists are actually able to figure out how far away these objects are. This is another kind of standard candle that allows us to map out the distances to various objects within our universe. And because planetary nebula are so much bigger physically than many of the other objects that we see in the sky that we use as standard candles, this allows us to start mapping out accurately the distances to nearby galaxies that haven't yet had supernova go off and are too far away to readily use Cepheid variables or other kinds of standard candle stars to measure the distances to the systems. So this is the kind of science that I kind of love in astronomy, where we have these amazingly beautiful images where we're getting straightforward science, and that science is applicable to answering some of our deepest questions of where we are in our universe. Now, moving on to how we see and understand things and measure the distances to things in our universe, there is a study that looks at how we can use X-ray radiation to figure out the distances to active galaxies. Now, this is research that was completed by C. Simons, J. Buchner, M. Salvato, L.T. Shu, and F.E. Bauer. They are scientists working in Chile, Germany, and Taiwan. These researchers have been looking at spectrographic data. This is data that tells us at these specific colors of light, the galaxy is either emitting extra light or absorbing extra light over and above its normal rainbow emission that is its black body radiation. In this case, they're looking at emission lines, lines of extra radiation that are located in the X-ray part of the spectrum of these galaxies. Now, X-ray light has the particularly good feature astronomically and bad feature for human beings of pretty much penetrating just about anything with high energies that has the potential to blow apart your DNA. This high energy radiation that goes through all the soft tissue of a human being also readily passes through dust and gas that otherwise might obscure these active galactic nuclei from being observed from here on Earth. There's a lot of places in our sky where we look and the material that makes up our own Milky Way galaxy gets in the way of letting us see outside of our galaxy. By looking in the X-ray, we can detect a variety of objects that are otherwise completely invisible. Working on looking at X-ray spectra, this team of researchers is finding which lines, which part of the spectra can be used to measure redshift, the rate at which galaxies in the distant universe are moving away from us. This is a measure that can also be used to tell us just how far away systems might be and help us understand when was our universe most active in terms of having galaxies undergoing mergers or star formation bursts or otherwise having activities going on that will drive material towards the galaxy's central supermassive black holes. And as this material falls in, it forms disks that are so thick, so dense, that nuclear processes go on within these disks, nuclear processes that we see here on Earth as those disks glow like distant stars. This is where the quasi-stellar object name has come from that gets applied to quasars. Now, what they're finding is they can take data from a variety of different satellites that work in a variety of different wavelengths of X-ray light, and in all cases get, with varying amounts of error, accurate representations of these galaxies' redshifts when they compare what they get in X-ray with results that have been gotten from normal visible parts of the spectrum. So in this case, they studied active galactic nuclei that can be seen in optical light, compared what was seen in optical with what can be seen in X-ray, measured the redshift of the system using both techniques, and this provided a calibration for how well the X-ray will work to measure the Doppler shift and thus the distance to objects that can only be seen in the X-ray. As you can see in the chart, you don't want to be using NuSTAR, which observes in highest energy hard X-rays, to be doing this kind of research if you want low X-ray error. Now, at the same time, the softer results, the soft X-ray, lower energy X-rays that are observed with SWIFT, with Athena and Chandra, all of these offer low error potential measurements. So by choosing your X-ray radiation colors correctly, by choosing to use the lower energy photons instead of the higher energy photons, accurate measurements can be made of where in the universe these obscured by dust objects happen to be located. Now, those were the main stories of interest that I saw in the peer-reviewed results. But there's a lot of results that came out today that looked intriguing and haven't gone through peer review. And I wanted to use this as an opportunity to explain what peer review is and how we select our stories here at the Daily Space. Now, in this cartoon, which I'm going to go in larger on so that you can read it. Oh, and it looks like I'm cutting off the edge of this graphic. One moment and I will fix that. So when I submit my research for peer review, it is sent out to a number of different individuals for review. This is typically 3 or more people. It can be as few as 1 in some journals. And these different reviewers read through the paper and make comments on whether the science is done well, whether the science is something that moves the field forward or is simply a replication of already known science. And based on how they interpret the paper within the context of the existing literature, their own expertise on the subject, they will make recommendations on, can this paper be published? Is this science good? Does it need extensive review? Does it need minor revisions to simply add some extra data, add some extra analysis? Or is it fine the way it is and should just get published? Now, one of the ongoing jokes that we make is reviewer 3 is always the kind of person you don't want to deal with, who makes all sorts of amazing demands and is hypercritical of everything you say or do. And this leads to the 5 stages of peer review, when you get your reviews backed and you are in denial of what that infamously awful reviewer 3 has to say, anger at reviewer 3, bargaining in terms of you resubmit the paper saying, well, I did these things, I didn't do these things, here is why. Please let my paper through. Depression that you're never actually going to get the paper done, because sometimes you can go through multiple years of going back and forth with a journal on whether or not they will publish your paper. Literally, you can submit a paper, get it back 6 months later in some cases with, you need to make all the following revisions. It might take you a few months to complete those revisions. You send it back in. Several months later, you get a, okay, this is better, but, and several years later, your results may finally make their way into the published peer-reviewed literature of your field. Now, some people choose to simply bypass this process, and they place their research on the internet in one of many different free repositories. In astronomy, we use the archive.org repository, and we submit our papers into what's called the AstroPH section. Now, every day I get a whole set of abstracts emailed to me of what are the latest papers to go into the archive. And looking through things today, I found, well, here in the most reasonable of the papers I flagged, there is a theorist who is discussing how it is we should consider whether or not we need to upgrade our theory of gravity to include additional components that act at great distances, so that instead of requiring dark energy and dark matter to understand the motions in our universe, we can instead, in this case, look at how gravitational vacuum polarization can have an impact because of different kinds of effects that were generated when our universe went through a brief period of inflation in the early days after the Big Bang. And by early days, I actually mean early minutes and hours after the Big Bang. Now, this paper hasn't even been submitted for peer review. It's simply put out on the archive as, here are my thoughts and ideas, and please read them and incorporate these ideas, cite these ideas in your research. People do this kind of just submit to the archive for a variety of different reasons. One of those reasons may be they don't want to wait the however many years that it takes for something to go through peer review. And while it's possible to submit your paper to archive to be shared the same day you submit your paper to a journal for peer review, some people are just like, it's not even worth going through that. So they just throw their ideas up. Another reason might be that they are a researcher that, well, like me, to be entirely honest, doesn't necessarily have all the funding one might wish for to be able to pay for the page charges that are part of publishing in many different journals. Now, the way I approach this is my research gets submitted to journals that you can generally publish in for free. Examples are the monthly notices of the Royal Astronomical Society is a journal that doesn't have page charges if one of the authors is a member of that professional society. Within the field of communicating astronomy, we have the CAP journal, which is funded through the International Astronomical Union. And it is, again, an entirely free journal. And with the CAP journal, they also disperse the journal entirely for free. With monthly notices, you have to pay for access to the journal articles. So there's a variety of different reasons that people might do this. But in some cases, it's simply because they don't think their research can necessarily get through peer review. So here I have an example of that kind of a theory paper that just might not make it through. And these particular papers are the ones that cause me the greatest frustration. So this is a paper on how what are called fast radio bursts might not have a explanation based on readily accepted physics. Fast radio bursts are pulses we sometimes serendipitously see in our radio observations, where we might be looking at a patch on the sky and suddenly get this massive high luminosity burst of radio emission. And we don't yet have a definitive explanation for why we see these. There are many different explanations. Some of them use normal everyday objects undergoing very rare kinds of physical events, or in this case, they're simply saying cosmic strings, which we have no observational evidence for, might be the explanation we need. And this particular paper goes through and discusses the kinds of things that should be taken into account in using this theoretical structure as an explanation. Now, when I read papers like this, I spend a fair amount of time considering the fact that I'm an observational astronomer. I have a good understanding of what it is I see when I look at data on variable stars, on galaxies and clusters, and how to interpret that data. But string theory and things like cosmic strings and theoretical particles that we don't have observational evidence for, that only exist in math. These are things that are beyond my personal area of expertise. So when I look at a paper like this that hasn't gone through peer review, I don't, as an individual, even as a PhD astrophysicist, have the ability to say if this is right or wrong and should be taken into consideration. And one of the benefits of peer review is, while it's an imperfect system, while it has a lot of bias in it, where papers from individuals at certain kinds of universities, papers from individuals from certain minority groups, including women and people of color, don't get the same kind of review that a senior white male at a top research university might get. The same benefit of the doubt isn't given. Peer review isn't perfect, but if something goes through peer review, I know that there are at least 3 experts in that field who have said this has a good chance of being true. So here at the Daily Space, we don't go into detail about these kinds of stories that haven't gone through peer review because we don't have that vetting process of other experts in these very specific narrow fields going through, reviewing these papers and saying, yes, I give credence to this kind of research. I think the results of this paper in the long term can be validated and have a good chance of being proven true. So things like this are speculative, they're interesting, they have brain-catching titles and sometimes even eye-catching imagery. But we generally don't cover them because we don't have the ability to say, this particular narrow area that is out of all of our expertise is something that we can really discuss. So this is where peer review is imperfect. It leads to a whole lot of emotional anguish. I know of at least one individual who's left the field of astronomy due to the bias and harassment that she faced while trying to publish her research. But some peer review in a flawed universe is better than no peer review. And in general, we will stick to trying to bring you the results of people working carefully and working within the context of having their peers assess their research, highlight ways their papers can be improved through further analysis, through further comparison to other results, and through further discussion and error analysis. We will take these results that have been hopefully improved through peer review and highlight them within our daily stories. So that's what I had to bring you today. And I completely forgot to switch back to a view that allowed you to see more than just the graphics. So thank you for sticking around during all of those boring, abstract, riddled conversations. And I am now here to take your questions. So pardon while I pull up the chat someplace big so I can more readily read it. And if you can go ahead and at me, I would appreciate. No audio? I see audio. Oh man, I'm so sorry for that. Okay. I will need to figure out exactly what went wrong because according to my screen, the audio that you get in this view and the audio that you get in the graphics only view should be identical audio. Yeah. I'm sorry that Amazon is torturing you, Hanny. That is deeply confusing. I will work to fix the audio issues. Okay. Well, do you have any science questions? And I apologize for the audio issues that you faced. And I will work to make sure, especially in this room where we're next to a busy road, that you get better quality. The webcam is, as you might guess from my lighting, right next to the office window, so it is getting a loud and clear transmission of all that's going out down on the road below. But do you have any science questions? And if you put in any earlier, if you could go ahead and repeat them, I'd appreciate it. So I see from Paranor that Hanny Zvorverp asked about the recent Einstein confirmation of distant galaxy. I thought we discussed that earlier this week, but I may have not. Wait, Einstein confirmation of a distant galaxy or of a triple system? So we've had a couple of different sets of new confirmations of relativity that were done. There was one case of looking at a lensing object that I believe Dr. Andreas Plazas covered in an episode of the Daily Space last week, and then earlier this week I covered a story on how gravity was tested in a triple system that contained a pulsar, or a special kind of neutron star, and a white dwarf in a close-in orbit that was about the separation of I don't remember what the separation was, but it had a less than 2-day period. And then there was a second white dwarf orbiting around this with a 300 plus day orbit. And both of these different theories were able to um, both of these different sets of observations were able to further confirm that our understanding of gravity is thus far completely true. Um, okay. So Hanny, I think we covered that particular story with Andreas's discussion last week of a gravitational lensing observation that was made. So all of our episodes are archived on YouTube, so please go check things out on YouTube. And I'm going to be working along with one of our research staff, Anya Gloshko, to make sure that we add in references on all of our show notes. So Phoenix asked, is there something wrong with gravity in the future? Well, we don't know about the future. This is one of the problems we have with science. We can see what was going on before. Telescopes are actually observational time machines that allow us to look into the past because light takes time to get here. When we look at the sun, we're looking 8 minutes back in history. When we look at Pluto, we're looking several hours back in history. As we look at star systems such as Alpha Centauri, we're starting to look several years into the past. And as we look out at Andromeda, we're seeing what was going on in Andromeda when the earliest humans were first beginning to walk on the planet Earth. So as we look further and further back, we're seeing what was going on in the distant past, allowing us to show, yes, the physics now is the same as the physics then. Now, over time, our universe is expanding, and we're seeing its structures changed. So far, physics has always stayed constant, but the interplay of dark energy, dark matter, and regular matter has changed over time, where we went from a universe where the gravitational pull of all of the matter within the universe and all the other matter in the universe was one of the dominant forces describing how our universe was evolving. And today, as we have a lower density, significantly larger universe to contend with, we are in a dark energy dominated universe. So we do see how all of the matter and energy in all of its various forms interplays, changes over time. I'm not sure I specifically answered your question, Phoenix, but I hope I at least danced around and gave you an idea of what you were getting at. Noel is asking, do white holes exist? No. What's inside of a black hole? Don't know. Physics doesn't get there. Are we living in a simulation? That is a personal opinion of which my answer is hell no. Can we travel backwards in time with a black hole? No. We can travel forwards in time by living through time at an accelerated rate. However, we will die in the process. When will we be installing EM drives on NASA rockets? Not going to happen, but you did, while you didn't have actual questions, hit on many of the questions that other people might be thinking and afraid to ask. So Uncle Bill has a aphelion day question. I recall a Verne character stating aphelion and perihelion as the reason some southern hemisphere seasons are more severe. Yes, that is actually true. The reason that Antarctica is a worse place than Arctica is not just the water being a thermal sink, although that does have something to do with it, but it also has to do with there is a diminutive difference in energy received during the southern hemisphere summer when we are closest to the sun in January, and the southern hemisphere, sorry, I said this backwards. We are closest to the sun at perihelion, and we are furthest at aphelion. And the closest occurs in January, the furthest is occurring now. So since we're furthest away during northern summer, our summers are a wee bit potentially gentler than the southern hemisphere ones when they are closest and receiving more energy. So it doesn't have to do with the tilt of the earth making you further or closer from the sun. It has to do with having both the tilt so that you have summer going on and being physically closer to the summer at the same time, driving your weather cycle. So, yeah, small things, but they add up to small changes in how we experience the seasons. Uh, I like the way DPI 209 commented on Noel's questions. Um, so the FR refers to a series of models, and there is no easy explanation I can give without doing a significant amount of research before trying to answer that question. So Larry is asking, do you do peer review of other authors? Yes, I actually got a request to peer review a paper earlier this week. So those are on the list of things I need to get done. I don't peer review as much as some authors do because since my personal work straddles education research, science research, and I spend far more time than many scientists would consider wise publicly communicating science. When you don't publish as much, you don't get asked to review as much. But just as I try and publish 1 or 2 papers a year, I usually get asked to review 1 or 2 papers a year. So it works. Peter, oh, you're quoting Dr. Paul. Okay. I don't know what Astro B. Oh, there it is. So Astro B, history is littered with theories and proposals for things that we now accept as very real, but were put down by so-called authorities and thinkers in their original launches. Yes. Dark matter was mocked openly for many years. And part of the issue may have been that the early observational evidence came from a very cranky person who is famous for being the reason for the phrase, and here, this, forgive my language, circular bastard. This is someone who is a bastard from all directions. Sorry, spherical, to get the words correctly. And this was at a point in history where we hadn't yet figured out we shouldn't use certain words to describe people because it's mean, and there's nothing wrong with that. So you had one very cranky scientist, and then the other scientist was a woman. So we had, that was Vera Rubin, and I'm completely failing to remember the name of the cranky scientist. He did the first catalog of irregular galaxies, and I feel terrible for not remembering his name. But when a new theory is first promoted by someone who is not a nice human, and by a woman at a time when that is not the best thing to be in the sciences, theories take longer to accept. So yeah, there are lots and lots of ideas that it took time to accept, and sometimes you actually have to just wait for somebody to die. This was the case with Eddington and Chandrasekhar, where Eddington did not like the idea of white dwarf stars and fought Chandrasekhar on their existence for decades. And after Eddington finally died, everyone was like, you go, Chandrasekhar. You nailed this scientific concept. It was similar for what is the actual Hubble constant, where we had two different scientists, one who was like, it is 50, and another who was like, it was 100. And they would redo everyone else's papers to suit their desired result. Um, it took it took death before we could settle on it's in the 60s. So Hanny is asking, why did matter form in dark matter halos? How did the matter come together first and dark matter form? That's it's a chicken and the egg problem where you have the wrong order of operations, I'm afraid. So when our universe first came into being, it was a mix. Well, it started out as pure energy, but then it became a mix of normal matter and dark matter. And this mixture, due to how the early universe evolved, had slight irregularities in the density of the material. And the dark matter quickly settled in to, oh, there's an irregularity over here. I shall flow into that irregularity if it's an overdensity and build a halo. And with it came the luminous matter that was in that, well, what would become the luminous matter, the regular matter in that region of the universe. So because there's more dark matter than luminous matter, we see this as the dark matter halos forming and attracting in more and more of the regular matter. Now, this was all going on at once, and so we probably confuse people with how we tell the story of galaxies forming within dark matter halos. It's more a matter of you have a small irregularity. Everything with the ability to be attracted by gravity falls into the irregularities that have a higher density and gets pulled out of the irregularities that had lower densities. There was a whole lot more dark matter than regular matter. And so we talk about the dark matter halos being the places that the regular matter fell into the center, formed stars and galaxies. The places with lower density were emptied out, formed voids. But it's just gravity pulled here and didn't pull back well enough over here in the void. So it's not that the matter formed in dark matter halos. The matter and the dark matter were all over the place, fairly evenly, but not completely evenly distributed in the initial formation of the universe. And over time, the irregularities evolved into the large-scale structure that we now see today. So I hope I explained that. So Henny's Warverp, seasons are driven by the intensity of the light. You totally got that correct. So I need to bring in a ball to my office. For now, I'm looking for something round. Aha, I'm going to use a soda can. Okay, so here I have a soda can. And if light hits up here, coming straight in, let me use a pencil to define straight in. The light is going to get spread over a larger area because it's coming in at a high angle. If light hits straight on, it's going to cover a smaller area. So when the pencil beam of light gets spread over a large area, you have fewer photons per square inch, per square meter. Whatever units you choose to use, there's going to be fewer photons per unit area. If the light comes straight in, it's going to have more light per unit area. In the summer, we have the sun closer to straight overhead. That pencil beam of light is significantly smaller. In the winter, we have the sun low down on the horizon. That pencil beam of light is spread out more. We have less light per unit area. So the seasons are related to how much light do we have per area on the ground. This is not at all related to our distance from the sun. The distance from the sun, which is a tiny, tiny, tiny effect, the distance from the sun, which is a tiny effect, will mean because we're closer to the sun, we're able to capture more of the sun's total radiation on the earth. So here it is. If you're closer to your light, you are blocking a larger amount of the light, casting a bigger shadow on the wall. If you're further away, you're capturing less of the light, creating a smaller shadow on the wall. So these are the things that go into affecting the seasons. Biggest effect, tilt of the earth, which causes the light to spread out over a smaller or larger area on the surface. Tiny, tiny, tiny effect, distance from the sun, that comes due to the fact that our orbit isn't a perfect circle. Tiny effect. Fritz Zwicky, yes, that is the name of the person who was not a nice man, and because he was not nice was part of why, due to human bias, dark matter didn't get accepted quite as fast as it probably should have. So Noel is asking, would the land to ocean ratios in the northern and southern hemispheres dominate over the influence of the changing distance? I don't know that answer. This is actually ongoing research, and the answer changes based on the amount of ice coverage. If you have a lot of ice, it's highly reflective, it scatters light off of it, and serves to keep the area colder. You melt the ice, and suddenly you have a heat reserve. So I don't know the current results. Just don't know. Sorry. It's ARPS. You're right. It's ARPS Irregular Galaxy. Zwicky was the first galaxy clusters. Sorry, wrong catalog. I meant Zwicky. So I see. Yeah, DPI. Some argue that new concepts take an entire generation, but it really depends on who makes the results. When we had two top-notch research university teams, so it's two teams consisting of people from top-notch universities, come out and say, there's this stuff called dark energy that is accelerating the expansion of the universe. There is a collective expletive from the entire field as we realized we now have to change our understanding of the universe. And it was very quickly given the Nobel Prize and accepted. And I was one of those people who uttered expletives because it meant I had to redo all the calculations in my doctoral dissertation. And I did not want to do that. But it was accepted so quickly that between 98 and me writing up things in 2001, I had to make sure every single thing was redone with our new understanding. So some theories we pick up and instantaneously, because of who it comes from and the kind of evidence, it's instant acceptance. Other things, due to either the kinds of evidence or, unfortunately, who it is bringing the theories forward, don't get noted. The saddest thing that can happen is you have a non-charismatic group of researchers who aren't entirely exciting writers publish a breakthrough concept. No one reads their paper because they don't want to. They don't present it at a whole bunch of conferences. And the idea doesn't get generally accepted until perhaps many years or even many decades later, somebody else who is charismatic, who may not even cite that original research, is like, oh my gosh, look at this thing. And then they get every award there is for changing the field. Science isn't always fair. Yeah, it's not always fair. Um, oh, ex legato. I I'm glad you finally found us. And the nice thing is, we are here Monday through Friday, except on major holidays. So, like Thanksgiving, Christmas, not going to be here. But outside of those kinds of exceptions, we are here every Monday through Friday to bring you the daily space. Now, I do have I've unfortunately eaten into Matt and Joe's time. I'm sorry, Matt and Joe. I'm an awful human being. Dr. Matt Richardson is sitting in the wings waiting to start a channel to teach you, as he teaches our own Big J, one of our software developers, astronomy. So Big J is a great programmer who just doesn't quite know the science behind the things he is coding. Matt Richardson is one of our scientists who is leaning on many of us to still learn how to code. And we learn from one another. And we invite you to be part of that and join in as Dr. Matt teaches Big J just how we know what we know about our universe. So stay tuned. This is a reminder, the daily space is part of CosmoQuest, and we invite you to visit cosmoquest.org. And in your spare time, instead of playing whatever your latest mobile app is, or actually don't try this on mobile, whatever your favorite laptop mind-numbing, time-passing game is, instead of playing that game, consider doing science. Consider joining us at cosmoquest.org to map out Moon, Mars, Mercury, Vesta, and even our own planet Earth, and identify the places that are safe to land, safe to live, and the places that are scientifically interesting to explore. CosmoQuest is organized through the Astronomical Society of the Pacific, and we are a multi-institutional collaboration. Here on CosmoQuest, you're going to see me, Dr. Andreas Plazas, and Big J, who are all employed by the ASP. You're also going to see Dr. Matt, who is part of the Planetary Science Institute, and Annie Wilson, who works at the Ward Beecher Planetarium at Youngstown State University. So go ahead, give us a follow. Find out and don't miss any of our episodes that go live. And we are sustained thanks to you. Your subscriptions really help us keep going, and every bit really matters. So thanks a lot, and please help us do science, and we will keep putting science in your brains. And now, don't go away. I'm going to press stop on my end, and Matt will be starting things on his, and the show will go on. So I will see you all Monday, wherever you are in the world. Have a great morning, evening, or afternoon, and remember, go outside and look up. Bye-bye.